Good day and welcome back for part 3 of our discussion on improper integrals. And let me begin with a reminder of where we left things in our previous video. We were discussing the so-called p integrals. And what we were able to observe is that based upon the value of p, we can immediately say whether the integral converges or diverges. In fact, we said this improper integral converges whenever p is strictly larger than 1, otherwise it diverges. So that would be when p is less than or equal to 1. With that in mind, let's move on to a new type of example and see if without evaluating this integral, can we determine if the improper integral is convergent or divergent? And our motivation, or kind of our approach for this problem, is to think about the following question. Can we compare this integrand with one of these p integrals? And then maybe make an observation based upon that comparison. So if we focus in on our integrand, x over x cubed plus 1. And I would like to remind you of an observation that we previously made back in Calculus 1. When we were dealing with limits of rational functions, we said the behavior is essentially determined by the largest term in the top and the largest term in the bottom. So with improper integrals and having to deal with this infinite interval, that is some good intuition to consider. What is the largest term in the top and the largest term in the bottom? This rational function is going to essentially behave like 1 over x squared. With that observation in mind, I would like you to pause the video and make a conjecture. Do you think this improper integral will converge, or do you think it will diverge? And my guess, or my conjecture, is if it's going to behave like 1 over x squared, and we're integrating from 1 to infinity, it should essentially behave like that corresponding integral. So our best guess is that it would converge. And what I'm going to need in order to convince ourselves that this is true is an inequality to work with. So I'm going to go ahead and make an observation. Let's go ahead and consider this function of interest, x over x cubed plus 1. On the interval we are dealing with, we know that our function is strictly going to be positive. Our x values are 1 and larger. I also know that I could get something bigger than this dividing by something smaller. And this is a key observation we will make over and over again in the upcoming weeks. Dividing by something smaller gives you back something larger. And just a quick observation in terms of this intuition, if you are unsure, consider a nice concrete example. And let me just make this observation to the side. If you were to consider something like 1/3 versus 1/2, I think we can all very confidently say 1/2 is larger than 1/3. Dividing by something smaller will give you a larger quantity. And in our case, this x over x cubed is 1 over x squared. So if we just think about this purely from a very intuitive graphical perspective, we're thinking about what happens from 1 to infinity. If we were to graph 1 over x squared, roughly it's this decreasing function. And in comparison, x over x cubed plus 1 is something which is always smaller than it. So in red we have x over x cubed plus 1. And the integral that we are interested in, this improper integral from 1 to infinity of x over x cubed plus 1. Geometrically, the value of that integral would be calculating the area underneath this red curve. And if you know the area under the blue curve is finite, because that associated integral is a convergent p-integral, the area under the red curve must be finite as well. So let's kind of just summarize this up in an observation. So our big takeaway here is that since 1 over infinity 1 over x squared converges, and we should always know why something converges if we're making that observation. So in this case, it's a p integral with p equals 2, which is larger than 1. So now from our geometric observation to the right, we can also note that the integral from 1 to infinity of x over x cubed plus 1 also converges. And it turns out that this is really an application of a property called the comparison test. So this comparison test I referenced for our previous example can be stated as follows. Suppose that f and g are continuous functions, and you know that g of x is always positive, and it's smaller than or equal to f of x. And let's go ahead and illustrate this graphically to help us make the desired observation. So once again, we're kind of thinking what happens from A to the right. We have a larger function, f of x in blue, and we have a smaller function, g of x in red. Let's think about the possibilities. If the improper integral from a to infinity of f of x converges, that would tell us that the area under this blue curve is finite. If the area under the blue curve is finite, then the only possibility would be that the area under the red curve is also finite. So if the larger function has an improper integral which converges, so does the smaller function. And just note the intuition. If the bigger thing converges, so does the smaller one. Now thinking of maybe the opposite perspective, if the area underneath this red curve is infinite, well, that infinite amount of area under the red curve is also enclosed by the blue curve. So if the improper integral of the smaller function diverges, then the same must be true of the larger. So once again, just to reiterate, if the bigger thing converges, so does the smaller. But if the smaller thing diverges, so does the larger. So that's the intuition, and really the graphical perspective to the right tells the story of why this is true, just thinking about enclosed area. Now, when it comes to using the comparison test, the remaining example that we see is a very common problem. Use the comparison test to determine if some improper integral converges or diverges. Now, the difficulty to using this comparison test is we are just given the one improper integral, i.e. this one function, and we have to come up with this inequality. And oftentimes, but I guess not always, but very frequently we will compare with these p integrals. And before getting too specific with this example, let me make an observation above that it is extremely important that our functions are positive. That's the only way we're allowed to make this geometric observation. So focusing in on this integrand of interest, let's see what observations we can make. So if we look at e to the x over the square root of x squared minus 1, what we can observe right away is that e to the x is something that gets really large very quickly. Graphically, if we want to visualize e to the x, we have the standard exponential growth curve, and note it goes through the y-axis at this point 0, 1. And we're thinking, specifically, what's happening to the right of 1? Well, one observation we could make about the exponential function to the right of 1 is it certainly lies above this red line, y equals 1. That is to say, e to the x is always bigger than or equal to 1 as long as we have positive inputs for x. So something smaller than e to the x would be 1. And there's two perfectly good ways to make a fraction smaller. You make the top smaller, or you make the bottom larger. So note, we made the top smaller, but we could also make the bottom larger. And dividing by something bigger gives you something smaller. Go back to that 1/3 versus 1/2 example. And note, I realize this is not an easy or even necessarily intuitive concept at first, but it's something that I think with practice is going to become quicker and more efficient. Also worth noting is the square root of x squared is x, and this is definitely always going to be positive. So now, thinking about what the comparison test is going to tell us based upon what we know about the integral of 1 over x. It diverges. And if the improper integral of the smaller function diverges, think this red shaded area above, then the improper integral of any larger function is also going to diverge. And we need to write this up a bit carefully. So we need to first make our observation. Since this improper integral from 1 to infinity of 1 over x dx diverges, and you need to tell me why, this is a p series with p equals 1, the comparison test, this new property of interest, implies that the larger improper integral, the one we are interested in, also diverges. So when it comes to using this comparison test, oftentimes the biggest difficulty involved is getting started. What type of observation can we make to somehow compare this integrand with one of our p integrals? Once we've made that comparison, as long as this inequality is in the right direction, we can apply the comparison test. And this is a problem that we will certainly encounter again in an upcoming video, but also in a different context coming up in the future. So make sure to spend some time practicing through the suggested problems. When you have questions, do not hesitate to reach out. So stay tuned. Take care.